Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. El-Moursy again for the recording of lectures for the Digital Logic Design DLD, and we are now in lecture number 18. This is part 2. We finished part 1 in the first recording. 18 part 1 we have finished. We have actually designed three circuits. We designed the basic block for the half adder, FA. We built the basic block for the full adder, as it is shown here. And from those two blocks, we have been able to engineer the problem and build what we call a multi-bit adder. In this case, we are showing a 4-bit adder. As we demonstrated in the part 1, we have used our standard way of design, the standard step of design, that are 5 steps that we have talked about them in lecture number 17, okay, in order to design the two basic blocks for the half adder and for the full adder. The functionality of the half adder and full adder should be crystal clear to the minds of the students, because we will use them later on for other purposes. However, some of you may ask a question here. So, if I can engineer the problem like that, okay, using the basic blocks, do I need to still learn the standard way of design? The answer is definitely yes. Without the standard way of design, the 5 steps that we learn to build any blocks, we cannot achieve this. This is one point. The other point is that there is an advantage in following the standard way of designing the basic blocks. And this should be clear for you. Since we are following the standard way of design, block diagram, TT, K-maps, equations, and then the circuit, we achieve a very important goal here, which is the optimization of the circuit. This circuit is optimized in terms of area and delay. Why? Because the circuit has been developed and designed through the standard way of design. This cannot be achieved by engineering the problem like this. So maybe somebody comes and asks me, so if my target is to design the 4-bit adder in the standard way. We indicated in the last lecture, in part number 1, that this is not practical because due to the huge truth table and the huge and large number of K-maps needed. However, if I'm using the computer tools and I follow the standard way to design the multi-bit adder, okay, how can I compare this adder to this 4-bit adder that we have designed, okay? Definitely, for the standard way of designing the 4-bit adder, I have pros and cons. The cons is that the design is not simple. The design needs some assistance of some computer tools. Okay, it needs significant amount of time in order to work with a truth table of 256 rows, working with 5 K-maps that are 8 variable dimensions. So it's a huge effort. Okay. However, this effort is paying off, because actually when I use the standard way to design the multi-bit adder, I will achieve the optimized design. So both the delay and the area will be the ideal, will be the minimum. The advantages that we have in the standard design is the disadvantage of this engineered design. Okay, so the design that we have done yesterday, or done in the first lecture here, okay, has actually nothing comes for free. Okay, this design is simple because we can build the block of the half adder, we can build the block of the full adder, and we can cascade them like this. But actually, what we have paid in order to see a realization of the design like that, the payment here is that neither the area nor the delay is optimized, because when you do not follow the standard way of design, there is no guarantee that you have reached the minimum area and the minimum delay. For the area, it's hard to tell, because actually we have to make the optimum design, follow the standard design in order to know the number of gates. But we can analyze the delay, the standard design, and this, okay, without even going into the design. The standard design for the 4-bit adder, if I follow the standard way of design, it's guaranteed that the delay will be 2 tau delay, because I will use the TT, the K-maps, and I get the minimum SOP and or the minimum POS for each of the equation of the outputs. So accordingly, the delay will be optimized to 2 tau delay time. Okay, what about this circuit? Okay, what is the delay of the circuit? Before I discuss the delay of the circuit, I need to do a little bit of modification for that circuit. We, in the last lecture, have built the half adder and the full adder. This is the design for the full adder. Can I replace the first block here from a half adder to a full adder? The answer is yes. But remember, in order for this circuit to work as before as an adder, the full adder has 3 inputs. So I have one extra input here. However, in the original equation, I have only inputs A0 and B0. Okay? So I will call this extra input, I will call it Cin. And I will set its value to 0. Now, effectively, the full adder acts exactly like a half adder. Because right now, although I have 3 inputs for the full adder, one of them is fixed to the value 0. So this adder will basically add in A0 to B0. Did I change anything in the functionality? The answer is no. Did I get the addition performed? It will be performed perfectly as before. What is the advantage of using all full adders here? The advantage is the simplicity in the design. Now I will go to the circuit engineer, ask him to design the full adder as we shown here just once. And I will ask him to replicate this block how many times? 4 times to get the circuit here. If I need an 8-bit adder, what shall I do? Just simply replicating more for full adders here. If I need 16-bit adder, we'll replicate the full adders again, and so on. So this mechanism can work. So one advantage of this design is the implementability and definitely the practicality, because we succeeded to do the design, and also the expandability. Okay, one of the very important advantages of this design is that if I need more bits to be added together, all what I have to do is to replicate more the full adders. No need for redesign. However, for this design, if I intend to change the circuit and I need 8-bit adder that adds 8 bits from A and 8 bits from B, what shall I do? I have to redesign the problem from the beginning with 16 inputs. Okay, this is definitely an impossible TT to follow the standard design for designing it. Okay, and it will have 9 outputs. So I have to deal with 9 K maps. Each of them has 16 different inputs. Impossible to be done. However, this way of design, which is called actually a ripple adder, okay, is doable, is implementable, okay, and we can design it very easy. But we have to pay something. The first payment is that since I didn't follow the standard way of design, there is no guarantee that they are optimized. But what about the delay? Okay, optimized delay give me guaranteed 2 tau delay. What about the delay of the circuit? Let's go and follow our thinking here. What is the delay of one full adder? The delay of one full adder It's a circuit designed using the standard way. So the delay of the full adder is 2 tau delay. Okay? So that means I have 2 tau delay for that adder. But what is the delay of the whole circuit? The delay of the whole circuit, remember that the output from the first full adder is an input to the second full adder. So in order to get the output here, the output of the circuit, I have to wait the signal to propagate the first full adder and enter the second full adder. In the second full adder, it has another 2 tau delay. In the third full adder, it has another 2 tau delay. In the fourth one, it has another 2 tau delay. So the propagation delay of the circuit here as a total, I'm looking for the critical path delay. So the critical path delay for the circuit is the longest delay of the circuit. So the delay to get the last output is called the C4. The total delay for my circuit is 8 tau delay. Nothing comes for free. Okay? Yes, I engineered the problem. I implemented the circuit, but I'm paying. I'm paying what? I'm paying delay. An optimized delay using the standard way will give you 2 tau delay. This engineered design that I have just designed has an 8 tau delay. Not only that, if I want to, instead of building a 4-bit adder, I want to go to 8-bit adder. So the delay will be multiply this by 2, so 16 tau delay. So the delay of the circuit is dependent on the number of bits to be added. So it is circuit dependent, which is definitely a disadvantage. Nothing comes for free. Yes, you succeeded to build the circuit, but you paid something in return. So this is actually all what we want to mention about the adder circuit that we have built. Now let's move on to our next item for the adder subtractor circuits. The second or the next circuit that we want to study is the subtractor. Okay, so let me just remove the design of the full adder that we have finished yesterday. Okay, we don't need it anymore. Okay, we already used the basic block for the full adder, and this is good enough. Okay, the detail of the design we already covered in our previous lecture. Okay, now I want to replace this by a 4-bit subtractor. A 4-bit subtractor. Four-bit subtractor. How can I build a 4-bit subtractor? Shall I go and design the circuit from the beginning? The answer is no. We already have learned how to do the subtract operation in chapter number 1. So let's go and review the operation of subtraction. How can I do a subtraction between two numbers? Okay, assuming that each of them is 4 bits or any number of bits. So right now I have A minus B. Do you still remember You still remember how we did the subtraction in chapter number 1? We didn't do actual subtraction, okay? Do you still remember the technique that we have learned, that we have utilized for a subtraction in chapter number 1? The technique is called what? It's called the complement technique. Okay, so in chapter number 1, we have succeeded to transfer or change the subtract operation by an addition. Okay, in chapter number 1, we mentioned that in order to subtract those numbers, I can just convert the operation from subtraction to an addition. How? To get what we call the 2's complement of the subtrahend. Okay? So 2's complement of B, when I added to A, will actually give me the result of the subtraction. We learned that in chapter 1. So how can I get the 2's complement of B? Two's complement of B have two ways to do. The regular way is that getting the 1's complement of B and adding 1. Go and review chapter number 1. A plus 1's complement of B is actually B bar, plus 1 is actually the 2's complement of B. So if I added A to the 1's complement of B, which is actually B bar, to 1, I will achieve the subtraction. We learned that in chapter number 1. This is a great method, because how can I get the B bar? B bar is B bar. B bar means the 1's complement of B. Means flipping each bit of B. Okay, if it is 0, I flip it to 1. If it is 1, I will flip it to 0. What is the circuit that allows me to do that? Yes, it is an inverter. Okay, so if I inverted each bit of B and I added the B bar to A and I added to all of this 1, I will achieve the subtraction. That means a very simple modification for the adder circuit can convert the operation from addition to subtraction. What are those changes? Two changes only. Instead of adding, so this circuit is actually adding A to B. However, I wanted to add A to B bar to the value 1. That's why Dr. Ali here have actually removed the first half adder and put a full adder, because this full adder gives me the capability to add 1 to the circuit. So if I change it Cin to 1, that means right now I'm adding A to B to 1. This is the first change. But actually I need to add A to B bar to 1. So how can I get the B bar? I can get the B bar simply putting inverters in front of B. Now the input B will be converted to B bar, A will remain the same, and the Cin equals to 1. So the circuit that we see right now after those modifications is not anymore performing an addition between A and B. On contrary, this circuit is actually performing some subtraction. So I converted the 4-bit adder to a 4-bit subtractor by simply changing the C in input here to 1 and changing the B to be B bar. So with this very simple small hack, okay, this circuit has been converted from a 4-bit adder to a 4-bit subtractor. That's it. Very simple. Okay. So now the design that we have on board, okay, needs first of all here the block diagram also needs to be changed. So we have here a subtractor, okay, and this subtractor has one extra input here called C in equals to 1. So adder with C in equals to 1 and B pass to an inverters, this will make the circuit a subtractor. So we are done with the for a multi-bit subtractor or 8-bit subtractor. Okay. Usually or easily, I can extend this design also in order to have what? To have more than 4 bits. I can make it 8 bits, 16 bits, whatever I need. Agreed? Make sense? Okay. So let's go to a more interesting design. We learn what is the 4-bit adder. We learn what is a 4-bit subtractor. Can I achieve both goals at the same time? Can I build a circuit that can be an adder and subtractor at the same time? This needs a little bit of thinking because it depends on the value for C in. Okay, so the inputs for the full adders should be changed. The inputs for the full adders should be changed. Now I need the input. The input for A for the full adders has no change. There is no change needed. Okay. Actually, the change that I'm looking for is that the input for the second input of the full adders. Okay, so A will remain the same. B, depending on the value of C in. C in actually can be of 2 values. C in could be 0 or 1. Correct? The second input for يبقى in2 for the full adders. I need into to be in2, and this is B. So I am looking for a circuit, not the inverters, because I need the output for this circuit to change based on the operation. If I'm using this circuit as an adder, C in should be 0. C in should be 0. And the inputs to the full adders should be B. So I need some circuit that when C in equals to 0, The circle here will give me exactly the value of B. It is just to do it with the coloring. I need to put some circuit here. The output of this circuit, when Cin equals to 0, will be identical to B. So it will give me B when Cin equals to 0. And the circuit will be an adder. When Cin equals to 1, I need to get B or B bar. I need a subtractor, so I'm looking for B bar. So if it is B is 0, it should give me 1. If B is 1, it should give me 0. So what is the circuit that I have to put here in order, and it has the two inputs, Cin and B. When Cin equals to 0, it will give me B. When Cin equals to 1, it will give me B bar. What kind of logic gate that I need to put here? Now, go back to the last lecture of chapter 3. We learn this logic gate. This logic gate is called, yes, correct, XOR. 0, 1, 1, 0. This is typical functionality of XOR. So all have to do is to put here in front of this circuit, I have to put here, instead of putting an inverter for the subtract, I will put an XOR. This XOR will be connected to the following inputs. One input for this XOR is coming from Cin. Cin. Three, and the circuit will act as an adder. Okay? Then what? When Cin, I change Cin to be 1. Right now, this line is actually having 1 at the Cin. 1, 1. Okay? So the new block that we have just shown is that neither for an adder nor for an subtractor. It's actually a circuit that is called adder slash subtractor. It works in both ways. It actually depends on the value for Cin. If Cin equals to 0, the circuit will be an adder. If Cin equals to 1, the circuit will be a subtractor. Okay? So it is very flexible. By only changing one input, I can switch between the adder and the subtractor. So this circuit is called adder slash subtractor circuit, 4-bit adder subtractor. And it can be easily extended by more full adders and XORs to give me a larger circuit. Okay? So when Cin equals, when Cin equals equal to 1, it will give me A plus B plus 1. When Cin equals to 0, it will give me simply A plus B. So that's why it's called the adder subtractor circuit. Agree? Make sense? I think this is enough. I just want you, as a homework, to think about how can I modify this circuit in order to detect the overflow case. If this is adder, is used for sign to complement. By the way, this adder subtractor circuit can work either I want to do addition subtraction for unsigned numbers or for signed numbers, because addition subtraction the step for the addition subtraction steps, forget about step 1 because they are matching in number of bits. Step 2 and step 3 are identical between the unsigned and signed, as we indicated in chapter number 1. However, okay, if the steps will start to change, to be different from the overflow. If I am using this for unsigned numbers, how can I detect the overflow? It's simply the C4. But if I wanted to use this to detect the overflow, well, assuming that the numbers A and B are signed to complement, okay, how can I do the circuit? Okay, let me do that, and I will leave the sign for you to do it at home. Now, I have these outputs, I have this circuit, and assuming that A and B are signed to complement numbers, and I want to detect the overflow. Do you still remember how we detect the overflow? Yes, detecting overflow for the sign to complement numbers is done through a comparison between the last two carries. Do you still remember that? When we do the still remember that, assuming that those are my numbers, okay, and I perform the addition between them, okay, and I know that the numbers are signed to complement, How can I detect the overflow? Do you still remember? We add those 0, 0, 0, 0, 1, 0, 1. How we detect the overflow for sign to complement? We compare between the last two carries. If they are similar, no overflow. If they are different, there is an overflow. From the circuit that I have here, can I detect the overflow? Yes. How? By comparing the last two carries. Where are the last two carries in the circuit? The last two carries do exist. Where they are? It is C3 and C4. How can I compare between C3 and C4 using the digital logic circuits in order to know whether they are similar or different? Okay, so similar or different means now again I will build a very small truth table to indicate the functionality that I am looking for. I have C3, C4, and I'm looking for the overflow bit, OF bit, overflow bit. Okay, I have a small tt here, four possible combinations 0, 1, 0, 1, 0, 0, 1, 1. The overflow bit should be 1 if those are different, and should be 0 if they are similar. Okay, so if they are similar, it should be 0. Similar should be 0. Different should be 1 and 1. So now I solved the problem for you. What is the logic gate that I have to put here in order to detect the overflow for sine to complement? The gate is simply as another XOR. كده ولا ايه؟ It's another XOR. An XOR will give me exactly what I'm looking for. So if I just simply take an XOR gate between C3 and C4, I will get here the overflow bit. Great. So we get the overflow bit. At home, think about design a logic circuit in order to detect the sign if the numbers are sine 2's complement. Okay. So we finish all the circuits for the addition subtraction. We learned the full adder, the half adder, the multi-bit adder, 4-bit adder, and 4-bit subtractor, and 4-bit adder subtractor. We also shed some light about how can I detect the overflow for signed numbers. And this is closing the lecture number 18. And the next lecture, inshallah, 19, we will go over the decoders, encoders, and the next one will be multiplexers and demultiplexers. Thank you.